My name is Fionn Lightfoot and this is my Physics 2211 Lab 3 on black holes. So first I'm going to be going over the purpose of my lab. The lab was split into two pieces of code. So section 1 was to analyse the motion of a star to determine the mass of a black hole. And the second part was to simulate the motion of a spaceship around a planet and its moon by calculating gravitational forces. Before I get into my code, I wanted to cover the fundamental concepts of physics first. So the main equation we'll be thinking about is Newton's second law. So this can be derived in many different ways, but if we start with the equation that I've put on the screen, we have F net is equal to the change of momentum over time. And then this can be derived further to separate F net into F net parallel and F net perpendicular. Then we also have the universal gravitational force, which is also created by Isaac Newton. So we have the force of gravity is the gravitational constant times mass 1 times mass 2 divided by the radius squared times r hat. And then we can rearrange this equation to get it in terms of a singular mass. So this is section 1 of my code. And as you can see, the seed is my Georgia Tech email. And then underneath we've got some system properties and initial conditions, including the gravitational constant, the mass of our star, delta t, which we chose to be a day, and the initial time. So then underneath this we have our initial conditions and final conditions, which is the initial momentum, final momentum, and then we've also got our final velocity and initial velocities, where we can then calculate the change in velocity and then the change in momentum, which will then allow us to calculate dp dt, which is also equivalent to F net. Now we're going to separate them into their different components, including dp dt parallel and then dp dt perpendicular. So this is where we calculated p hat, which is used in both, and then we're able to combine F net perpendicular and F net parallel, and then you're able to do the mass of the black hole as needed. So this is what the product of our code was. As you can see, the green line is the circular orbit of this mass orbiting this black hole in the middle, and the arrows are just showing the different components. For example, the smaller magenta arrow is the p hat direction, which is following the circular trajectory, and then the orange arrow is pointing towards the black hole, which is n hat. So then all of this code for section 2 is basically just finding the net forces on the moon and the net forces on the ship. I was able to do this based off the universal gravitational equation, which I could then calculate all of these, and then I was able to do the change of velocities by trial and error. This was the image that my code produced, and you can see that there's an orbit of the spaceship and an orbit of the moon, and this was created from the code and the different velocities that I chose. Some possible errors we may have encountered would be the use of approximations. So since we're just using a simulation, it won't actually represent the reality of what a black hole would actually do or a mass orbiting a black hole. And then some assumptions we've used is there's no external forces which would greatly impact our calculations, as there's going to be air resistance as the planets are moving. And then finally, we have trial and error in choosing our velocities. So in order for the code to work, we had to choose many different velocities. So some would work, some wouldn't, and then we chose the final one, which isn't very realistic. So the first question we're going to ask is, what does it mean? And this is net force versus change in momentum. So numerically and mathematically, they are actually the same thing. But to find the change in momentum of an object, all you really need to know is the change in the object's velocity or motion, and it's very easy to separate the components as I showed in the third slide. Whereas net force, you need to know every external force acting on the object, so then you can resolve forces into parallel and perpendicular forces, which can be a lot more time consuming. And then finally, the question of what if. What if our system now contains a black hole as well as the other components that we'd already been working with? So then you would have to include the gravitation of the planet around the black hole. Since the mass of a black hole is so big, all other objects would orbit around it as a central feature. Thank you for listening to my physics lab.